Welcome back to the Explainer. So today we're diving straight into Type 3, displacement. Or honestly, I like to call it the reactivity battle. Because if you thought chemistry was just, peacefully mixing liquids in a beaker, well, get ready for a serious change of pace. We're looking at elements literally fighting for dominance in a chemical compound. It's kind of like a microscopic Game of Thrones out there, and in this world, only the strongest survive. So grab your notes because things are about to get really competitive.
So what actually is a displacement reaction? At its core, it's exactly what it sounds like. A more reactive element comes in and displaces, basically just vigorously kicks out a less reactive element from its compound. Think of it like a super aggressive game of musical chairs. But here, the chairs are the molecular bonds, and the heavier, stronger players, they just completely shove the weaker ones out of the way to take their seat. It is entirely about hierarchy and power. The stronger element comes in, takes over the compound, and sends the weaker element packing into total isolation.
Okay, let's step a little deeper into this chemical arena. We're really looking at a fundamental law of nature here, where elements are fighting for their place based entirely on their inherent chemical strength. Because, let's face it, not all metals are created equal. Some are eager, super aggressive, and highly reactive. They're always looking to form a bond. Others are much more passive, docile, and stable. And when you mix those two wildly different types of metals in a solution, a battle immediately kicks off. And in this arena, there are no ties. There's always a clear winner and a clear loser.
To really picture how this battle plays out, let's walk through a classic experiment. You probably remember this from your NCERT activities. Imagine this highly visual, three-step process happening right in front of you. Step 1. You take a standard, shiny, sturdy gray iron nail and dip it into a beaker filled with copper sulphate solution. Now, copper sulphate is really beautiful to look at. It's this vibrant, bright blue liquid. But just watch what happens in Step 2. As the minutes tick by, that brilliant blue color slowly, almost magically, starts fading away. It gets paler and paler, turning almost colorless or like a faint pale green. And then, Step 3. You pull the nail out of the beaker and no way, it's no longer that shiny gray iron. It's covered in a rough, reddish-brown coating. That coating, it is pure copper. The iron literally ripped the copper out of the solution and took its place.
And this equation right here brilliantly illustrates exactly what's happening at the microscopic atomic level. It basically reads like a story. You've got Fe, solid iron, plus CuSO₄, aqueous copper sulfate, yielding FeSO₄, aqueous iron sulfate, plus solid Cu, copper. You can literally see the displacement happening right there. The iron marches right up to that copper sulfate compound, boots the copper out, and bonds with the sulfate itself. Iron completely takes the throne, becoming iron sulfate, while the poor copper is left all by itself as a solitary solid. And that isolated solid copper, that is exactly what makes up that brown, rusty-looking coating we just saw clinging to the nail.
So the absolutely crucial rule to remember here, and the ultimate answer to exactly why iron displaces copper metal in this scenario, is this. Iron is simply more reactive than copper, period, so it displaces it. It all comes down to their internal atomic makeup and their desire to bond. Iron atoms are just chemically driven to lose their outer electrons and form ionic bonds way more than copper atoms are. Copper is relatively unreactive. I mean, that's exactly why humans have used it for water pipes and coins for centuries, right? It just likes to stay as it is. Iron, on the other hand, is hungry for reaction. Because of this higher reactivity, iron exerts a much stronger chemical pull. It easily overpowers the copper, forces it out, and takes its place in the sulfate compound. The stronger, more reactive metal wins every single time.
Now, what's really interesting about this is that iron isn't the only bully in the chemical schoolyard. Let's introduce another fierce competitor to the arena, zinc. Look closely at this comparison. The top equation is our familiar iron battling copper and winning. But check out the bottom equation. That shows solid zinc, Zn, being added to that exact same bright blue copper sulfate solution. And the result? The exact same kind of devastating outcome for copper. The zinc displaces the copper, forming zinc sulfate, ZnSO₄, and leaving solid copper behind. Both iron and zinc play the exact same dominant role against copper. It really just proves that in the grand hierarchy of metals, copper is sitting pretty low on the totem pole.
So, why does all of this matter for you? Well, especially if you're gearing up for your CBSE exams or just want to truly master chemistry, understanding this rule gives you a literal superpower. Here is your ultimate CBSE tip. You can predict if a reaction will occur just based on metal reactivity. You don't have to actually mix dangerous chemicals in a lab to know what's going to happen. If a question asks you, hey, will a reaction occur if I drop silver into iron sulfate, you can look into the chemical future.
If the solid metal you drop in is stronger and more reactive than the metal already sitting in the compound, boom, a violent reaction happens. If it's weaker, absolutely nothing happens. The solution just sits there completely undisturbed.
But how do you know who is stronger without just guessing? You need the ultimate chemical cheat sheet, the reactivity series. You absolutely have to memorize this hierarchy if you want to know who wins any chemical battle. Let's energetically run down this list of power. At the very top, the undisputed heavyweight champions, potassium, K, and sodium, Na. They are so violently reactive they literally explode in water. Then we move down through calcium, magnesium, and aluminum, arriving at our tough guys, zinc and iron. Keep going down past lead and hydrogen, and look who's near the very bottom. There's copper, followed by silver and gold. Gold is so unreactive it stays shiny for thousands of years without ever forming a compound. By memorizing this exact order, you hold the key to predicting every single displacement battle in the book.
All right, so we've completely mastered single displacement, one strong, aggressive element kicking out a weaker one. But I want to leave you with a fascinating kind of mind-bending question to ponder. What if two compounds swap partners instead? Like, what if it isn't just one element taking over, but a mutual exchange, a highly coordinated chemical square dance where everyone changes partners at exactly the same time? That is the wild world of double displacement, and that's exactly what we'll be decoding in our next explainer. Until then, keep analyzing those reactions, get that series memorized, and thank you so much for hanging out with me on the explainer.